a video walkthrough for Audification of a phylogeny. Go to github.com chesters.phylogenetics phylogeny. And first thing, just download all these files here. You get a zip file, just put it into some working directory, and then here's all some of the tools you will need, and open up the sort of bash commands. So let's take a look at this. Assuming a Linux or something similar. Now, unfortunately, there are a lot of dependencies for this. It's rather involved. So you need R. You need these 3 R libraries installed. I know that's a bit awkward. 2 Perl scripts, process Nuke, and this should be provided just in that thing you just downloaded. 2 R scripts, and there's a Linux command line tool which is for various media processing. This quite a popular audio processing software, and 2 text files. Additionally, I would also recommended is tree viewing software for doing various processing. Okay, so first thing is we need machine readable trees phylogenies to Audify. You may have one of your own you want to do, or maybe you want to get some. So the first thought might be is to go to some publication. Actually, that's not really what we want, because we want machine readable tree and we need a Creative Commons license which allows us to do other things with the data and potentially republish it. Actually, what we want is probably the main source from these is a data repository. Particularly Dryad has a lot of these. So the default license for Dryad and I think Figshare is Creative Commons. The other ones I'm not sure, but so go to Dryad and search for phylogeny and you'll find so here's a typical landing page for a data set of supplemental data. So you're looking for machine readable trees. Typically these have a .tre extension, you can see here. Now as you can see, there's a bunch of them, so which one to choose is a bit complicated. So the authors ideally we want a ultrametric tree. The reason for having ultrametric tree is it's already rooted is the main thing, so it's one less step to do. Potentially also you might have a bit more information content in that. If it's not ultrametric, it's very common for authors, regardless of what is in the main text, they will upload a unrooted tree, so you actually have to go and reroute it yourself, which is an additional processing step which can be a bit awkward. So for finding ultrametric, you're looking for words like for ultrametric time tree, MCMC, astral, I think sometimes is ultrametric, and dated. Okay, so we have one here, dated. So this and .tre. So this is a good bet for a ultrametric machine readable tree. So let's have a look at this. Move this into our working directory. And first let's just take a look. So you can see this is, yeah, I'm kind of glad this one came up. This is a rather complex format. In fact, it's even difficult to, there's so much information on the node IDs, it's even difficult to find. Even I can't even see a terminal label here. Okay, so here's a terminal label. So this is Nexus format. So Nexus format is a bit more complex. So it always starts with a Nexus, and we have taxon labels, and there's a key, so you get a number and the label itself. Also, I see a problem here. This might cause some issue, some weird characters. But anyway, well, firstly, we need, so this is difficult to read, so we'll try a couple of tree views, which hopefully they can read this. So as I state here, I suggest 2 tree views, fig tree and Archaeopteryx. Archaeopteryx is very scalable, so even if you work with very large phylogenies, you should have no problem. There is, however, one specific subtle format change which confuses Archaeopteryx, and in that case, fig tree will work. But with these 2 software, you should be able to read anything. So let's try Archaeopteryx first. So we need to order the subtrees, and we need to check the root. For simplicity, I'll skip that step, but we should find the main text corresponding to this study and just check what is at the root. Here it is the same as this machine readable tree. If it's not, then we have to click here, root reboot, and root in the appropriate location. But for now, we'll just assume this is correct. So as I say, order subtrees to give some consistent format. Order means that the clades are ordered according to the size of the clades, and that means always the smaller clades are at the upper, larger clades are at the lower. This gives some consistency in the audification. So you know that high tones are going to be smaller clades, low tones are going to be the larger clades. A bit more information content there. So we will save tree, and let's just call it Beck 2022. We need to choose Newick. So Beck 2022 is going to be the input tree. The control file, which shouldn't need to change anything in that. And let's now run the Perl script to interpret the Newick structure as a set of vectors. So I'll just copy these. Okay, the output is called vidify table 2. There's a bunch of other stuff which can be ignored. But okay, it just seems to have run. So we have the positions of the branches have here been interpreted as vectors, i.e. single lines, X and Y for the start and the end. Last is simply a count of number of terminals, which is sometimes used. So we need the R script Audify phylogeny. Copy that command into the shell. Now, how long this will take, it depends on the size of the phylogeny. Well, that's it didn't seem to be too big, maybe 100 or 200. I didn't really check. Let's have a quick look through what this is doing. I'd say a couple of our libraries are required. These variables probably won't change in. So in the earlier version, I just had a tone corresponding to where a split occurred. What I do now is I have a pitch shifting tone corresponding to the branch, the positions and the direction of the branch. So I call this pitch shifting because the shift is going up or down depending on depending on what the branch looks like. If there's a lot of descendants in a short time, you'll get a noticeable pitch shift. Now there's various scaling of the vectors, and I'll say there's a bunch of variables. Now these are automatically determined. I've been gradually refining these variables work pretty well according to how many branches. So as you get to a lot of branches, you need to, firstly, you can't try and audify all of them, because it just becomes just a mass, a tonal mass or something. You can't really differentiate anything. So you need to sample, and also you need to decay the tone depending on how many branches. If there's not many splits happening, then you can afford a long tone. But if you have a lot of branches happening summertime, you need to have much sharper tones to be able to discern one after the other. And also the track length, you can extend that also to get a bit more resolution in when you get a lot of tones for large phylogeny. So at the moment it's set for, it's either 30 second, 60 second or 120 seconds depending on the size. So if present, any previous analysis will be deleted. All the previous audio tracks deleted here. Here it's making a decision on if it's a small phylogeny, all tones will be printed. If it's a larger one, it was deciding if it's a long branch, that's an important one, so that will be noticed if it was missed, so that should be plotted or audified. If it's to the left hand side, you tend to get fewer tones, so these will be preferentially audified. If it's a large clade, also preferentially audify, which are the main considerations, and that seems to work pretty well. There's probably a better way to do it, which I've thought of, but haven't got around to that, but this works okay. So as for the turning a given branch to an audio file, the main things is you need silence before the tone starts. And now if it's right at the start of the file, then you don't have this, you won't have any silence. And if you put 0 here, there will be cases it will crash, hence this strangely long number. Anyway, for most of the branches, you first start off with a silence object, and the duration is to where the branch, obviously where the bifurcation starts. This one is, I'll skip that. That's for near the end, which you tend to get a lot of tones or a lot of branches, and those are a bit simpler. But here's a main code for. So you can see it's actually a bit more complicated than, well, it is what it is. So so as I say, this firstly, it's pitch shifting according to the direction of the vector. Now it doesn't. That's not continuous. Actually, what it does is it'll make segments. It's actually stepping up and down in these segments. Now, the reason you may want to do this is it actually corresponds. For many cases, it may not make much difference, but it means where the tone is going up and tone is going down, if you segment them and step the pitch shift, then you can actually audibly sometimes notice the correspondence between the increasing and the decreasing tone, i.e. these steps happen at the same time. And anyway, that's how it was done. But here's the main component here, where a tone is created for a given Y position. As I say, this is scaled according between about 200 and 900, which is the audible range, and this happens over a series of segments. Then you need to use this command whenever you attach two waveforms together. You need to prepcom the end of what you're attaching and the start of the next thing, or you get a slight sound at the attachment point. So we're creating the wave object. That's going into this item here. And the other thing I would point out is the decay that's happening here. So we have the wave item, and we are decreasing the amplitude according to the decay factor. So I say this is depicted in a manuscript, the manuscript about this. This is important in differentiate or resolving when you have a lot of tones. And finally, you get the silence after the branch has ended. That's also attached to, it's attached here to the item wave 1. I need to normalize, and finally that is written as a audio file here. So this happens for every single branch. And finally, so this is finished now, and it should be in the working directory a whole load of, you can see them here. These are all these are one for each audio file. So let's go back to so we've done this now. We have one audio file for each tone. So as manual steps, I did try this possibly could be done by the command line. I did try this, it really sounded rather messy, so I still recommend for this you can just use Audacity to do this step. So launch Audacity. This is open source software, so easy to find this. So file, import audio, and this is what you want to import. These are all the there's one audio file for each branch. So select all of these, and they should be called pitch shifting and maybe something after. So select all the pitch shifting file, and these will be imported. So depending on obviously the size of the phylogeny is how many files you have here, and this will take some time. Now these are rather large files, so this takes a while to import. For some reason Audacity doesn't have a progress box for this particular task, but it is working, and when it's finished importing, just one little tip, you can see there's no scroll bar on the side of here. When it's finished importing, the scroll bar will appear. So let's just wait for this. Okay, so as you can see the scroll bar appears here. So we have now finished importing all these files. Select all, tracks, mix, mix and render to mix these together. Now you can see the amplitude and it goes way beyond the top. So there's a couple of things we need to do. Go to effect. Now firstly, this is generally recommended. I'm not certain how essential this is. Lower frequencies are naturally a bit quieter, so it's generally recommended to increase the bass. So go to bass and treble and increase the bass a little bit. Now, I'm not sure how essential that is if you're uploading to a online platform which does its own processing and quite complex, and maybe they account for that themselves. I'm not sure about that. Certainly something you do need to do is normalize, and you can see this will look something like this. And finally we need to export. I usually export as WAV. This always works fine for me. And let's call it back 2022. And click OK, and that should be exported. Now I can close this. So now we have this single audio file here. And this seems to be kind of what we expect. Okay, so that's the important thing. Now what we can do, we can actually make a video corresponding to the audio files, maybe a bit more frivolous, but nonetheless, we can quickly go through this. So this is the plot frames our code. So let's copy that into here. So plot frames, it needs some particular plot tricks. And it needs a Perl script which does some processing in the working directory. There will be an error message here if it's not been put in there. But again, for the so this is not making a video per se. This is making a bunch of frames corresponding to the audification. Again, it checks the size of the tree. The size of the tree is determined how long your audio files are. Hence, you need to adjust the number of frames plotted to match that. But what it's doing is going along the x-axis and shifting the plotting window accordingly, plotting any branches which get up to that point, and also just for, well, make it look a bit more pretty, is plotting points at the terminus, at each position along the video. And it does somewhere here some sampling, so to make there's actually a series of points that you can see here, and there's actually a series of points plotted at different colors to make it look a bit more nice. And the size of these points depending on the number of terminals and how many points are at that given position. But so you can see it's plotting frames, so the default video frame rate is about 24-25, so that you'll get 24 times the number of seconds, and that's how many frames you'll have. So you can see here I given frame at a given position along the x-axis corresponding to the audio time. It's rendering a series of images. Now this can be a bit slow. So you'll have something like either 800 or 1600 or about 3100 individual frames depending on the size of the tree. So you need to combine the frames. So here we use the last three jobs are combining the frames to a video. We're using FFmpeg. You can see it searches for the this string, and you get all the frames are individual numbered, and puts those into this file. Then you can combine the audio and video. These should be pretty much exactly the same length if everything's gone to plan. So then you end up with the audio video MP4. And finally, I suggest adding subtitles with a single title. So I changed the font size. For the default subtitles don't look great. It looks a bit more stylish if you reduce the font size. But I suggest adding the title with the phylogeny name on there, because if you're doing a lot now, if you use certain online platforms for making it available and certain apps for uploading to those platforms, sometimes it doesn't actually show you the file name while you're doing it. But if you have the title of the particular phylogeny, then you're not gonna. You have some other reference point to what you. This is when you're dealing with a lot of them. So this is what a typical subtitles file looks like. It just has the subtitle number. It gives how many seconds start and end that is added, and then you just put the say the phylogeny name in here. Then you can use the FFmpeg to add that. So this is sometimes called burning, because this is permanent. This way is permanently added to the video file. And then this is the command here for doing that. So this is finished now. So for this size phylogeny, default will be 1625 frames. That is 25 frames per second multiplied by track length, which is 60 seconds on the tree, but additional 5 seconds kind of fade out at the end. So that will number 1625. So let's combine all of these frames into a video. Next, combine the video MPEG file with the audio WAV file, which should be both exactly 65 seconds long. Let's get the correct name for the audio file. We called it Beck 2022. Finally, subtitle, recommend, and simple format. Let's just put the title Beck et al. 2022 at the bottom of the screen for 5 seconds at the start of the video. Finished. Let's look at our result. So you can see some multiplications and okay, that is done. That's the audification of Beck et al. Phylogeny. Not sure I pointed out at the start, but this is very important here. License is Creative Commons 0. This means we can do anything we want with this. This can be republished, but of course we should cite this if we do that, and that's all.